Okay, this is a lecture on analysis of variance, otherwise known as ANOVA. So let's look back first. We look at t-tests to examine differences between just two measures. And so one measure could be a population parameter and another a sample statistic, or two independent samples, or two related measures, or a dependent samples t-test. So what about when there's more than two measures? That's when we have the ANOVA situation, when we have more than two measures that we're looking at. So ANOVA is to the rescue when we have more than two, and we have the same kind of hypo testing or hypothesis testing procedure to use to evaluate the mean differences between two or more groups. So it's the same kind of logic that follows for hypothesis testing. And this is a major advantage, that you can look at beyond more than two groups, more than just male versus female, etc. So, advantages of ANOVA. First, two or more groups or levels of the IV, so you can have two or more levels of the IV. You can do an independent or repeated measures design, so it's flexible in that sense, or you can have both where it's mixed. You can have multiple IVs. Now, please note that these IVs would be categorical and not continuous. If you had a continuous IV, you would be doing a different sort of analysis. So like if you were doing like a regression, basically. If it was just a continuous IV and a continuous dependent variable, that would be basic regression. So stating our hypos. How do we state our hypos in ANOVA? Well, first our null hypothesis would be H sub O, or subscript O, mu sub 1 equals mu sub 2 equals mu sub 3, where mu refers to, again, the population parameter of the mean. So we're saying that the means are all equal for these three groups. So let's say, freshmen, sophomore, juniors. So that would be one example. Alternatively, we can state that at least, our alternative or research hypothesis would be that at least one population mean is different from another. So at least mu sub 1, mu sub 2, mu sub 3, at least one of those is different. Now more than one could be, so that's another way of thinking of it. So comparing T to F. To calculate T, we look at the obtained difference between two samples over the standard error. And to calculate F, we look at the variance between, or differences between sample means over the variances expected with no treatment. So it's very similar, but it relies more on the variance, calculation of variance, or the analysis of variance, hence the name. So what's the logic of ANOVA? Well, the first step is to determine your total variability, determine the maximum amount of variability in your data set. Second step is to determine the between treatments variability. So the between treatments is, well, looking at your different grouping, let's say freshman, sophomore, senior, or male, female, or whatever. We wouldn't do it in male, female because, why wouldn't do that? Is because a t-test would be more appropriate in that sense. But so you have two or more groups, so looking at the differences between the groups. So that's the second step, to determine the between treatments variance. And the third step is to look at the within treatments variance. So this remaining part that remains after partialing out the between treatments variability. We want to know the amount of variation that is attributable by group differences or between group differences, because that's what we're interested in as researchers. We want to know how much of the differences in academic achievement or coping styles is a function of whatever independent variable. So we can come to two conclusions: that the differences are related to or caused by the treatment. And when I say related, that means it's a correlational study, or caused by, that would trigger you to think about an experimental design, by the treatment, or the differences are due to chance. And we hope that the differences are not due to chance, if, as a researcher. But that would be our null hypothesis, that it's all due to chance. So Within treatments, estimation provides a measure of how much difference is reasonable to expect by chance. So the figure for the book would be that there's total variability, and within that there's between treatments variance, which we would want to maximize that, and then within treatments variance, which we want to minimize that. Because within treatments variance is basically chance or some other fluctuation. Between treatments variance would be measures differences due to the actual treatment effects, but there is an element of chance in that too, of randomness there too. So, before getting into calculating an actual ANOVA, we've gone over the logic. We need to talk about some particular notation so we don't get confused later on. K equals the number of treatment conditions. N equals the number of participants per treatment. So I should go back. K, so number of treatment conditions. So if you have 3 groups or 4 groups, so let's say we did freshman, sophomore, junior, senior, K would equal 4 in that case. Number of treatments, participants per treatment, so the number of freshmen, the number of sophomores, the number of juniors, the number of seniors. So it'd be like N sub 1, N sub 2, N sub 3, N sub 4 in that case. And N equals the total of participants, or K multiplied by N when they're, it's an equal N. So in that case, so adding up freshmen, sophomore, junior, seniors. And T is the total or summation of scores per treatment. So you can look up and add up all the summation of scores per treatment. And G is the summation of scores of the total. So T is the per treatment total, and G is like the grand total. And actually that's usually what it's referred to as the G is the grand total. So let's look at an example. Looking at performance, there are 3 different temperature conditions. So we have condition 1, which is 50 degrees, hopefully Fahrenheit, because that'd be really hot Celsius. 2, 70 degrees Fahrenheit, and then 3, 90 degrees Fahrenheit. And there are the data, the performance of each individual. So you have the rows for each individual. Yeah. And then they summate a lot of it for you. So you see the summation of x squared equals 106, summation G equals 30, N equals 15, K equals 3. You can go back and make sure you understand the notation by calculating it how you think it should be calculated and see if it matches up to those numbers. So, but they've already done a lot of that work for you though. First up, we calculate the total variation, or the SST, which is the sums of squared subtotal, or SS sub t is sums of squared total, which is the summation of x squared minus g squared over n. So for our example, it would be 106 minus 30 squared over 15, or otherwise 106 minus 60, which equals 46. So the sums of squared total is 46. Now how did I get that number? The previous slide, they'd already summated or made summations for you for those numbers. So we just calculated the total variability, the SST. Next, we need to calculate the within or between treatment variability. You can calculate either first, it really doesn't matter. Well, I'm going to go ahead and calculate within treatments with the summation of inside of sums of squared variance inside each treatment. So for our example, it would be 6 plus 4 equals 16, and those numbers again come from the table previously mentioned. And for between treatments variability, you can calculate it simply by sums of square total minus sums of square within. So you see why I did sums of square within first. So that would be SSB, or sums of square between, is 46 minus 16 equals 30. Alternatively, we can calculate that sums of square between, if you want to do it first, as n multiplied by sums of squared for the means. From this alternative formula, we can calculate sums of squares of mean, and so using the computational formula for sums of squares, just to review, is the summation of x squared over summation of x parentheses squared over n. And so you can do this worked example where 18 is the sums of square for x minus 6 squared, 6 being the mean, over 3, which equals 18 minus 12 equals 6. So in that sense, so sum squared between can also be calculated with 5 by 6 equals 30. And alternatively, you can do summation of t squared over n minus g squared, or grand total over n as well. So for example, just giving you an alternative way of thinking about it. So it'd be 5 squared over 5 plus 20 squared over 5, then 5 squared over 5, and then 30 minus 30 squared over 5, which results in 5 plus 80 plus 5 minus 60, which is 90 minus 60 and equals 30. So you can arrive at the same conclusion. So you can see that SSB can be calculated a couple different ways. Choose whatever one is more comfortable for you, or alternatively just calculate sums of square within first, and then you can just do SST minus SSW and then get your sums of square between. Next, we need to calculate our degrees of freedom for total, between, and within. So you're going to have 3 different values for degrees of freedom. So your total degrees of freedom would be the big N minus 1. So the whole sample size minus 1. The within treatments degrees of freedom, or degrees of freedom within, would be N big N minus K, and K being the number of treatment conditions. So in this case it'd be 4, looking back at the example of freshmen, sophomore, junior, seniors. Or if you want to go back to the recent example, the 3 different temperature conditions would be 3 in that case, the K value. So in between treatments, degrees of freedom would be K minus 1. So in the temperature example, it would be 3 minus 1. So after getting our SST value, our SSB value, and SSW value, then we can calculate the mean square between and within. So mean square, we do sums of squares divided by degrees of freedom. So for mean square between, it'd be sums of square between divided by degrees of freedom between. So how do you think we calculate MSW? It's mean squares, which would be sums of square within over degrees of freedom within. Finally, we can calculate our F statistic value looking at the mean square between over the mean square within. A standard way of presenting this is in the table provided below. See the source between treatments and within treatments and total, and you'd provide a column of the sums of square values, and a column of the degrees of freedom values, then a column of the mean square values, and then the resulting F test statistic value. You would refer to an F chart to find your critical value. So you need to know 3 pieces of information to do this. The level of significance, that shouldn't surprise you. Usually 0.05 or 0.01. The degrees of freedom in the denominator, which is, the within, and the degrees of freedom within the numerator, which is the between. And then you can look up your F critical value, and compare that to your F statistic value. We can calculate R squared also as our effect size. R squared equals sums of square between over sums of square total. So it's kind of a close approximation of an R squared value. So for our example, it'd be 50 over 82, which would give you the value 0.16 or 61%, saying that 61% of the variance in performance can be accounted for by temperature. So what are some assumptions of ANOVA? None of these should surprise you either, based upon your understanding of T. First, observations. Sorry about that. I got a call. So observations must be independent. Observations must be normally distributed. And homogeneity of variances, that their variances must be homogeneous rather than heterogeneous. I can't say it all of a sudden. Okay, so post hoc test. Once we find significance ANOVA, the dance isn't over. We're still dancing with ANOVA. because we don't know exactly where the significance is. Unlike in an independent samples or any kind of T, you know where the difference is because there's only two groups. So you know that's where the difference is, that there is a difference between males and females because there's only males and females in the group in the analysis. So we have to remember our hypos because you don't want to do every single, your research hypotheses, that is. You don't want to do every single difference in the world because then it's more like a fishing expedition. Like I'm going to compare freshmen to sophomore, then sophomores to seniors, then juniors to freshmen, so it can become a fishing expedition, or a euphemism for that is exploratory, or data driven. That's another euphemism for it. So in performing your post hoc tests, be careful because there's a possibility of increasing your type 1 error rate over many tests. The more tests you do, you'll increase your type 1 error rate. This is also referred to as your experiment-wise or family-wise alpha level being increased. But post hoc tests are the way to determine where exactly your significance is, and there are many different types of post hoc tests that are used, and different people have different preferences, researchers that is, have different preferences for which test procedure to use. Gravner and Walnell covers, they kind of focus on the Tukey's HSD, or honest significant difference, and the Chaffee test. And Chaffee is the more conservative test in looking for differences. It's less likely to give you an advantageous result, meaning significance. These two are very popular, though, of course, for different reasons. And I think that's why they focus on them, because a lot of people use them. So looking at Tukey's HSD, it uses a Q value based upon a Q chart. So you get another distribution. So you have an F distribution, a T distribution, and now a Q distribution. And you calculate the HSD, or honest significant difference, as Q. You take the Q critical value from the chart that you would obtain, multiplied by the square root of mean square within over n. So this information you already have the mean square within value, so that it's an easy calculation after you've done all the work for an ANOVA. And n is the number of scores in each treatment, just to reiterate. And to locate the correct Q value, you must know the number of treatments, K, the degrees of freedom for the MS within, and your alpha level. So this is all really easily obtainable information after you've already done the work to do the ANOVA. And then you can compute your Q critical value, or use your Q critical value to compute your HSD value. Then you look at the mean difference compared to your Q critical value to the one you calculated. So in this case, it would be 3.53 multiplied by the square root, or multiplied by 4 over 9, the square root of that value equals 2.36. And our Q critical value is then 2.36. Yeah. Okay. We would then consider differences of 2.36 and greater to be different. So looking at this example, just to walk you through it, which comparisons would be significant? So in this one, it'd be like treatment A is significantly different from treatment B. The mean difference, mean sub A minus mean sub B, is 2.44. So is that significant? No, doesn't exceed the Q critical value that you just calculated based upon the chart Q critical value. But basically you're getting a Q critical value from the chart and you're adjusting it to the circumstances of your data. And then so number one is no, not significant. Treatment A is also significantly different from treatment C. And you need to look at that. So M sub A minus M sub C equals 4.0. So is this difference significant? Yes, it is. Yeah. Oh, wait, I messed you guys up. 2.44 is larger than 2.36. I don't know. My mind just went there for a second. So 4 and 2.44 are greater than 2.36. And our final one is treatment B is not significantly different than treatment C. So mean sub B minus mean sub C equals 1.56. So 1.56 is less than 2.36. So sorry. Okay. Last but not least, the Chaffee test is very conservative. Chaffee is considered more safe. smallest risk of type 1 error. Scheffé test requires you calculate a new symptom square mean square with between NF ratio for each comparison, so that's not pleasant. Uses the same formulas, but you only calculate it based upon the groups you're comparing. So just those two groups that you're comparing. Once you calculate each F value for each comparison, F A sub V, A, group A versus group B, then you compare them to the F critical value. You achieve this FCV value by looking it up based upon the degrees of freedom for the entire study, not just your comparison, and then your alpha level. Okay, well that was the lecture on ANOVA. Good luck on your homework.